Okay, we're moving now to next speaker, Andrea Annoni from Cordon Group.
Thank you. There is a USB key port. I have it on the USB. I wasn't able to do it this morning.
Shall we copy it?
Yeah, sure. There is a presentation in the PDF. You could copy both in case of some compatibility problems as we know.
It's not showing up.
No, it should be here. And no se reconoce. It was working, huh?
It was working before, but now it says
Okay.
now. Okay. Now it's there.
No, you just copy everything.
Let's copy this here. To this. Okay. Put it down.
Yeah, it's a little bit big, the presentation. Too many,
It's fine,
too many
it's
photos.
fine. Now it's opening, and then I'm gonna be Georgia.
Okay, thank you. Take it. Okay. Good morning, everybody. I'm Andrea Annoni. I work at Cordon Electronics, and I will present this presentation entitled Photonic Packaging for Telecom, Aerospace, and Defense, and more. Our company is located in North Italy. We are active currently in the telecom, aerospace, and defense markets. And we use microwave photonics and, of course, microwave photonics technologies. And we offer services as design, engineering, and manufacturing. We account for 85 people in our business unit, and we have a 2,000 class 10,000 clean room. As I was saying, we are manufacturing, but we are counter-manufacturing, so we don't have products per se in the catalog. We build our products based on specs of our customers. Can be built to specs, so they simply arrive with high-level specification, or they have already in mind what they need, and we perform the assembly and the testing. And we have now automatic equipment for pick and place and wire bonding and microwave testing optical bench. So regarding what I would like to talk in this presentation is packaging. I'm an optical engineer and come from, say, telecom background. And what I saw is that sometimes, especially if we are talking about something for telecom, datacom, so very high speed, the packaging is envisioned as something that can be done easily after the dies are fabricated and tested. So you have all these bits, you put everything together, and you get your whatever is needed, whatever it is one. The problem is that the more everyone would like, let's say, more speed, more complex devices, more compact and whatever. But of course, putting everything together with very high performance creates lots of problems. So if you want to go very high with your performance, you need also to plan ahead when you want, what you want to do with your packaging. And this is why currently people want to integrate everything inside. Lots of functions, so of course the PIC and your optical interconnection, but also control electronics, maybe something high speed, high frequency RF electronics, and in case you do not have, you have a passive PIC, you also want to integrate maybe a hybrid integration of laser diodes, photodiodes, and so on. And the problem is that all these technologies comes from different worlds. So you have your chip with some micrometric waveguide, but on the other side, if you want RF connection, you also have RF substrate that can easily go up to centimeter and so on. Or if you want electronic board, you have centimeter long electronic boards. So it's complicated to put all these things together. You start from the micrometric and you go up to centimeter. Also, all these components, all these devices are, you know, you need lots of different tools, and you also need lots of, different know-how. And it's very hard to have everything at hand for everyone. So what happens usually in the design process of, let's say, complex packaging is that you start from, of course, your specification, then you do the design, and at the end you go for the assembly. But the design process has an iterative nature. So you have all these stages: RF design, optical design, mechanical design, and in case, depending on the application, also multi-physical analysis. And every one of these aspects affects somehow the performance of the device. So depending on your result here, maybe you need to go back and, let's say, modifying your layout, your design. You have to compromise. You have some trade-off to carry on. Also, not let's say, negligible problem is that the mechanical design is one guy, the optical design is another guy, and the RF design is another guy, and not necessarily talk the same technical language. So sometimes it's also hard to understand one each other. So what happens, for example, is that you perform your design, then you do some multi-physics simulation, can be RF, optical, thermal, mechanical, whatever. And in case if you get acceptable results, so you don't have any strange results in your simulation, you can go forward, and then you evaluate what are your performance. If you do not have acceptable performance at the end, of course, you have to go back and decide what you want to do with your design, if you want to change the material, if you want to change the layout or the components or whatever. So I would like you to show here some example that when things are not optimized for packaging, specific for the RF design, which is from what I saw, the most complex stage. To not do any wrong to anyone, I will comment only on three cases that were not caused by bad design of the PIC, of course, but because there were some let's say, major constraints that force the layout of the PICs to be like that. And I have three cases when we used a PIC that was designed for a different application, when the layout cannot be changed due to the nature of the device, or in a case in which we had lots of space constraints. So, first case, we needed to assemble a transmission optical subassembly with this PIC. Is a double-side emitting laser with integrated electroabsorption modulator. But the customer required, I want only one RF side and one optical side. So all the input and output of the RF must be at this side, and here I want one optical output. This PIC was designed for another package. As you can see, we have RF on one side and RF on the other side, and on the two short sides, the two optical beams that must be multiplexed also in polarization. So the optical design was kind of tricky also, but pretty straightforward. So micro-optical lenses and isolators and so on, and half wavelength plate to multiplex with a beam combiner to rotate the polarization and to use a polarization beam combiner to combine them at the output. Okay, pretty straightforward. The problems arise with the RF design in this case, because you cannot go on the side of the PIC because you have the beam. So you will clip one beam or the other. You cannot go below because you have the ground below the PIC is metallized. So you need necessarily to go above. And in this case, we designed these flexible coplanar waveguides for RF, are based on, don't remember if gold or copper in a polyimide substrate. They are quite broadband, compact, very good performance. For example, the problem is that they have a very, very few supplier, long lead time, they are quite expensive, and still they are pretty much delicate, and we would like to understand more the reliability of these flexible coplanar waveguides. Another example I would like to show you is this. It's for traveling wave Mach-Zehnder modulator on indium phosphide. used for a dual polarization phase quadrature modulation. And the problem is that we cannot reach easily these two in the middle, because we cannot go on the sides because it was hybridly integrated with two other peaks, and we cannot go with the tracks on the peaks because it's full of waveguides and so on. So we need to reach these two that are in the innermost one, but we cannot perform, of course, wire bondings because it's too long, and we cannot flip chip drivers on top due to space constraint, and mostly because these devices are sensible to thermal crosstalk and thermal gradient. That is not the best thing to attack high-speed frequency electronics on top of that. So with the DTU, we designed this aluminum nitride RF interposer that was flip-chipped. It's not a problem because it's passive, does not dissipate power. And at the end, we get very cool results. Last case I would like to show you is when you have lots of space constraints. So 17 photodiodes with a 250 micrometer pitch. Wasn't easy because you cannot, let's say, use a classical approach here, because you need also to provide bias. You need, of course, you need the RF tracks to read the signal, and also you need the determination for the adapting. For the matching of the impedance, and it is not possible to place all these components, which must be near anyway to the photodiodes, with a 250 micrometer pitch. So you can use flexible coplanar waveguide, but it will look like this. It's very complicated, very expensive, and not very reliable. So what we decided to proceed is this. This is how we decided to proceed. A first layer of a bottom RF substrate that has the tracks to read the signal from the photodiode, and we place on top another substrate that carries the matching resistor and the DC block to avoid, let's say, passage of current when you also give the bias to the photodiode. You can see here in the side view how it is placed. So the photodiode, the bottom RF, then some spacer, and then you have the top and the top RF substrate, and then of course, you proceed with classical wire bonding. These spacers are needed because you can, of course, you have part of the field that goes above the RF waveguide, so you want to avoid interference. It's like an optical waveguide, in fact. It can be used for sensing, but it's not. It's better if it doesn't sense anything here. So we proceed with the simulations to see what was the minimum acceptable height of the spacers to do not have any effect. In case here with 127 micrometer, which is anyway very short, we already had less than 0.1 dB of excess insertion losses, so it's a good result. What would be the best approach? What would be the most sound approach is to include the peak layout as something that can be, of course, changed within the design process. But of course, this is usually carried out by someone else, a customer. We don't design the peak that we package. So it could be that you have too many back and forth with your customer, and you go very long with your time. So most sound approach is to have, let's say, that when you want to do your peak layout is to have two sets of rules, of course. The foundry rules, so you avoid to do something that you cannot fabricate, and to do a packaging rule, so like a PDK for packaging to avoid anything that then you cannot easily package. And currently we are developing this one for our, let's say, technologies. Okay. So let's get more in the core of this presentation. I would like to show you some packaging types that we did here for a different, let's say, final customer. Let's say I would like to divide this, let's say, this type of user one, the telecom, and the defense and aerospace. So starting from the user, as you can, user is someone that needs to package a die. does not have any specific markets. It's just a proof of concept maybe in the lab, because they cannot anymore go with bare dies on the optical bench, which is always one complicated. Usually they expect a short delivery time, or at least as short as possible, as humanly possible. The requested performance can vary a lot, so you can have someone that, I don't care, just a proof of concept, or on the other side, maybe they need very high speed or something that is very, very challenging. Can be both. Usually, these peaks come from multi-wafer project, multi-project wafers, so you get one shot. You have very few dies, maybe not all of them are good dies, and you only get this one, and it's better to get it straight the first time. This kind of request usually to us come from universities, companies, or big enterprises. And sometimes, not usually, not always, but maybe the customer does not have any idea about what packages implies. So for example, what we do usually is to have these two approaches, package one and a chip on board one. Package one is, let's say, compact. We have this standard package, 52 DC connection and 4 RF inputs up to 40 gigahertz. It's good for many different peaks. It's not constraints to a particular technology, indium phosphide or silicon. Can accept a lot of dimensions and a lot of technologies. And when the customer doesn't care about space constraints, so they can have something very big, or maybe because they need a lot of, as you can see here, RF connection of type that is not compact, to say the least. We can go for a chip-on-board approach where you have a base, you mount your die, and you attach and electrically connect boards for all the electrical connection. This one, for example, was developed for a European project called Spirit. Of course, you can also integrate something in either the package or the chip on board. So in case this is another standard package, but inside we had RF driver, the matching resistor, the PIC. Another PIC basically is a glass interposer to adapt the mode and the pitch, and to have like a RF driver with 6.25 gigahertz inside the package, or a very smart board with the clock generation up to 6 gigahertz and a USB port that you can use and connect to another computer and use a LabVIEW software that we developed to talk to the board. And basically this is a setup engineered only in 20 centimeter. Or if you want, you can go, of course, for something that is custom. You hear me? Okay. Something that is custom for the like this package that hosted hybrid integrated several hybrid integrated PICs, indium phosphide, polyboard, a laser, and also RF drivers. So telecom, I expected let's say higher volumes. Longer initial development time is not a problem, but at the end the process must be fast and cheap. And of course you have these kind of standards and the Cordia standards. These devices usually, in our case, use this kind of process. So we build up the micro-optical bench, we perform the die attach, the placement of the collimating lens of the isolator of the etalon mirror and so on, and we do this with our equipment we have in-house for fiber coupling and lens soldering, lens gluing, and active alignment. This is a short example of what we did for a customer. It's external cavity tunable laser on all the C-band with more than 13 dBm optical power output. And you have, of course, your etalon, your isolator here, your collimating lens. Here you have your gain chip, etc., etc., etc. Or another one, this is a tunable optical trap multiplexer that uses a SOI chip, so it's a silicon on insulator, and to perform extraction or addition of 4 VDM channels in the C-band. And was built inside and was packaged inside a CFP2 standard. And also you have, as you can see here, a lot of quite interesting electronic board to control your device. And we use an MPO standard connector for the optical output. So more in details, I would like to show you this one because it's more interesting. Defense and aerospace application. These are two applications that can be seen as harsh environment application. So you have vibration, stresses, temperature, presence of radiation, lots of things, very strict standard, and other constraints like assembly operator must be qualified, but at the end, accept quite high cost is not a problem. This is a case study that we did for a European project. It's called Optima. It's for satellite payload. It's a 40 GHz bandwidth modulator employing using a co-package DFB here on a micro-optical bench and a lithium niobate 40 GHz modulator. And these are the experimental performance that we get at the end. So how you can work in this kind of environment with a careful design. For example, if we talk about the mechanical design, you can design this package to have to resist to the vibration. You can avoid the panel-like structure, or you can get sharp. You need sharp 90-degree corners inside to increase the rigidity of the whole package. And when you have to screw it, just provide, for example, the most possible screws to even all the strains on the package. Otherwise, it would try to bend. And you perform, of course, a modal vibration simulation to see where it vibrates. Usually, it's between constraints are do not avoid this kind of, let's say, resonances between 0 and 2000 Hertz. In this case, these are the first two modes at which the package vibrates. Or you can also perform a static analysis, static load analysis of the package. This is, of course, increase the effect, but this is to study how your package change the shape when you have some mechanical stress. Also, of course, you need to work a lot on the process. In this case, for example, for the micro-optical bench, we avoided the glue. Everything was soldered with mechanical, let's say, laser soldering, like the lenses, or with alloys here for the components to avoid outgassing, increase repeatability, and so on, to increase the thermal conductivity. Also, you need to design your process flow using these alloys with different melting temperature. So you start from the bottom and you avoid to refuse all the previous soldering. Then you perform, of course, reliability test with the equipment you have in-house for vibration, thermal analysis, or leakage tests. And at the end, you perform a simulation to see how your package works. So multi-physics simulation, you get this input, design, temperature, and material properties. You studied your static thermal field, the steady thermal field, and you see how this affects the mechanical displacement. So at the end, what you get is like, this is the temperature of the optical bench when the tech is on, and the outside is, I don't remember if this one is minus 40, minus 20. And you see how this thermal field affects the displacement of your micro-optical components. Okay, you can see here the shade of the previous displacement and the new one. Of course, this is greatly exaggerated. And then you go from this simulation to another simulation. You can see everyone recognizes this software, I think. With the input of the previous simulation, you can study the effect of your of this temperature condition on your optical alignment, for example. Thank you.
Okay, thank you for this very interesting talk. Now there is time for a few questions.
Thank Thank you for the interesting talk. So earlier you talked about RF routing using flexible RF CPW lines. Can you please tell about how much is the RF bandwidth you can achieve by using these flexible CPW lines?
I think this one was for 28 gigabaud. So we're talking about 25, 30 gigahertz, 30 gigahertz.
Mm-hmm. And does this bending affect your bandwidth?
If it is not critical, not that much.
Okay.
Here you have a lot of, let's say, the degrees of freedom. You can change, of course, the gap and the width of the track. You can confine more or less the electromagnetic mode inside the coplanar waveguide, so it is more or less affected by the strain that you apply to the RF waveguide. Of course, just like an optical waveguide, basically, you can confine more or less the mode, and it will look more or less outside of the waveguide. In here, the most problematic was the space constraints due to the package that was required. In this case, was everything. This is more. Everything here was integrated in 15 millimeter by 8 by I don't remember if 6 or something like that. So kind of compact.
Yeah, and these CPW lines are flip chip bonded, if I'm right.
Are?
So do you flip chip bond these
I think
lines?
it was bonded by thermal compression. I'm not a process guy, so I just know thermal compression.
Okay.
No, they were not soldered. It's like you place them and then you go down with a probe or something with let's say a tool, and then you basically fuse the material together. It was not soldered or something like that.
Thank you.
Next.
So I have a question on, so a lot of things you show are very custom-made style. Right?
Yeah, but I work for the R&D, not for the production.
No,
so
I understand, yeah.
I solve problems.
Yeah, no, I fully understand, yeah. But for this to move forward, what kind of, let's say, where do you think the standardization needs to happen for this to really move forward a lot? You were talking about PDKs, that is basically standardization of pads, basically. Foundries might have standardized already, let's say, a building block like a modulator or something. So that is on die level. But do you think you need a higher level of standardization? Do you need sub-assemblies, packages to be more like electronics?
Probably the different types of packaging, or anyway the functions that are required by the customer are so completely diverse that it's kind of difficult to think of something like that, because one will need one modulator, other one will need two nested in phase and quadrature, the other one 4, so phase and quadrature is completely, it's kind of general rules to understand that there is something beside the peak. You can design, for example, the best modulators, but if you place these 4 modulators one beside the other, and you need a matching network, it's complicated. So it's is like a standard in terms of it's difficult to express. I mean, the applications are so diverse that it's you cannot perform a general standard that is written, or is more, let's say, common knowledge, I would say, to understand that there is something after that.
Okay, let's thanks Andrea again.
Okay.